Okay, everyone. Thank you for coming back. Let's do some problems. Let's continue to do some problems. We're still working on practice physics problems from the Katz book, Calculus Treatment of Physics. We're doing electricity and magnetism, calculus treatment thereof, from the Katz book, first edition. From the Katz book, first edition, chapter 26 problems, pages 821 to 826. These are the problems that will scroll at the end of the video that I've done. Similar procedure that I've done on numerous videos that we have seen. Not necessarily on all the videos, but on numerous videos we've done something like this. The problems that will be scrolling at the end are problems from chapter 26, the Katz book, problems 10, 11, 12, 13, 18, 32, 43, 48, 54, 69, 78, 81. Of those, 8 of them I'm going to try to do and get filmed doing them, and those are going to be problems 11, 12, 13, 18, 43, 54, 69, 78. So, okay, let's take a look at it. I'll start with number 11. Number 11, what is the work that a generator must do to move 1.80 times 10 to the 10 protons from a location with electrical potential 12.8 volts, 12.4 volts. So, what is the work that a generator must do to move 1.80 times 10 to the 10 protons from a location with electric potential 12.4 volts to a location with electric potential 43.0 volts? You're going to take it to a higher potential. To take it to a higher potential, you've got to fight the electric field that is going to oppose what is going on there. So essentially, a lot of ways you can look at it. So for 11, the change in potential, delta V, is the voltage at the final destination minus the voltage at the initial destination. So you've got this. (43.0) minus 12.4. The work, well, you got to remember, a number of things here. Basically, essentially, the voltage, so there's a lot of ways you can write this here. The potential difference is the work done per charge, per unit charge, work per unit charge. So if you just do the simple mathematics related to all that, you can find what work is by saying Q delta V. And that's going to be equal to, so you're working right with this. You're going to move 1.8 times 10 to the 10th protons. Each one's got a charge. That's how many protons you got. Each one of those protons has a charge of this. And you're going to multiply that by the potential difference. So let me erase what we said here. We know what we're going to be doing. We have this. So we know this. Okay, so let me erase that. For we know it. We do know this, what we have to do, so we're okay. And let's just proceed from here. Times the potential difference. Well, you did the subtraction there, 43 minus 12.4, 43 minus 12.4 is 30.6. All MKS system agrees. And what do you got to do? Work that's got to get done to do this. (8.8128) times 10 to the negative 8 joules to get the job done. And there it is. That was 11. 12. 12. How far should a positive 3.0 microcoulomb charged particle be from a negative 5.5 microcoulomb charged particle so that the electric potential energy of the pair of particles is negative 0.90 joules? So this is an interesting matter here, guys. Again, let's read it again. How far should a positive 3.0 microcoulomb charged particle be from a negative 5.5 microcoulomb charged particle so that the electric potential energy of the pair of particles is negative 0.90 joules? Okay. Well, there's a potential energy there. And there's a lot of ways that you can talk about energy. So frequently in much of what we do, there's got to be a consistency. In any of the physical sciences, when they're talking about something, they set up a procedure for what something's got to be, what it is. And then they kind of take it from there. So let's sort of look at this, kind of get a little bit of background on the whole matter, and then kind of look at it and see what we can say about it. Okay, well, this whole thing about potential energy is kind of a fascinating matter in its own right. I mean, how you want to look at it. What is it? What is it not? I guess you could say. The further apart they are, the greater the potential energy, though you wouldn't know it by a negative symbol there. The less negative something is, the closer that it gets to zero, if it's two particles like this that have opposite signs, the closer it gets to zero is going to be like essentially its maximum potential energy. It'll never really be there. It'd have to be infinitely far apart. But if you did, it'd be something along those lines. Okay, there's a lot of argument as to how you could conceivably do this. As we said in other matters, when we were talking about the absolute Kelvin temperature scale, we could have any temperature scale we wanted, as long as it was consistent with zero pressure being 0 degrees on that absolute temperature scale, and then proceed upward and then have that linear relationship going on in relation to pressure and stuff. So zero pressure would be 0 on the Kelvin temperature scale, or on any other absolute zero temperature scale that you'd want to make up for that matter. So there's a lot you can do. For now, let's work with their system. We know that essentially if you do a number of things, if you want to figure out the potential energy, you're using U sub E equals K Q1 Q2 over R. You want to get a negative 0.9, how about just negative 0.9? At that point, here's K, here's Q1, here's Q2, here's R. True. So just replace that with all the appropriate numbers associated with the actual problem. And you're talking about, you can use 8.99. I used 9 right here. It's not really a big deal. Usually if the book has been using 8.99 times 10 to the 9th, that's what you're going to use. Being that I wrote the problem in the notes in this manner, let me stay consistent with it. At least let me stay consistent with it. One is positive 3 microcoulombs, which is 3 times 10 to the negative 6. And the other one is negative 5.5 microcoulombs. Negative 5.5 microcoulombs and 3 microcoulombs. What distance apart do they have to be for that to work? The rest is pretty basic mathematics at that point, you guys. You're taking the R, you're multiplying by R on each side and dividing by the negative 0.9. Yeah, we got all that. Grind out the numbers, guys, and we're done. So you got R is equal to 0.165 meters and that's it. That's the end of it. Had the distance been greater, this negative number wouldn't have been this negative number. It would have been another negative number with the same circumstances had R been greater, and it would have been a negative number that had a smaller magnitude than negative 0.9 that you see over there. It would still be a negative number, but its absolute value would be smaller. Yeah, well, true, smaller magnitude. What's going on here? Smaller magnitude, but as you go toward negative, as you go toward 0, the potential energy, I guess you could say, that's there, if you were to release them, it's like dropping a shot put from a height of 1 meter, or dropping a shot put from into the sand, and dropping a shot put into some experimental facility from a height of 200 meters and no air resistance. The further away you are, the more potential energy is. So there'd be more potential energy here, and the negative would be indicative of that. So, kind of an interesting matter how that works out. It's almost counterintuitive in a sense. So you got to kind of just watch out for that. That was problem 12. Problem number 13. A proton is fired from very far away directly at a fixed particle. The particle is like locked in somewhere. It's not going to move. It's not going to be moved from there because of the proton coming at it. Otherwise it would be. But here it's not. So it's a hypothetical situation. A proton is fired from very far away directly at a fixed particle with charge Q equals 1.28 times 10 to the negative 18 coulombs. If the initial speed of the proton is 2.4 times 10 to the 5th meters per second, what is its distance of closest approach to the fixed particle? The mass of a proton is 1.67 times 10 to the negative 27 kilograms. So let's get to this. So what's going on? How's this working? Look, the way to look at it is this. There's a proton which is positively charged and it's fired from very far away. Very far away is, at that point, there's not a significant amount of potential energy because they're both positive. When they're both negative, there is a significant, when one's positive, one's negative, there's a significant amount of potential energy. Whereas if they're both positive, if they're close together, there's a lot of potential energy there. So that's kind of, it's again, it's something you got to kind of look at, but the mathematics is consistent and it does describe the situation. For our purposes, a proton is fired from very far away directly at a fixed particle with charge Q equals 1.28 times 10 to the negative 18 coulombs. That's a positive particle that's fixed, that's locked in somewhere, and it's not going to move because of the proton moving. The proton may be moving right at it, but it's not going to get moved because that Q equals 1.28 times 10 to the negative 18 coulombs. That charged particle of that charge is not going to be moved. If the initial speed of the proton, when it all starts out from very far away, is 2.4 times 10 to the fifth meters per second, what is its distance of closest approach to the fixed particle? The mass of the proton is 1.67 times 10 to the negative 27 kilograms. What they're talking about here is it's all kinetic energy in the beginning, no potential energy. Why is it no potential energy? Because it's very, very, very far away. If it's very, very far away, this is kind of weird. Zero means something big when the charges are of opposite sign, but zero means something genuinely small, meaning zero. I mean, they're both mean. Zero means something relatively big, so to speak, if we're talking about a negative particle and a negatively charged particle and a positively charged particle. And if they're very far away, it's approaching from negative values. From negative values, it's approaching the value of zero. Okay, it's approaching a very big potential energy. What are you talking about? How's zero big? Well, zero is bigger than negative 0.9. It's bigger than negative 2.6. It's a bigger number. I'd rather have zero amount of money than owe $225, than be down negative 225. So in that sense, it works. One's positive, one's negative. If they're both positive, you're going to get your maximum potential energy. The closer the two particles are, then they're going to want to fire out. So you got to kind of watch it. The equation works. The equation I showed earlier for problem 12 definitely works in all circumstances. Just, again, some caution is required and you got to be aware of the circumstances. From far away, there's no potential associated with the two particles. There's no potential energy associated with the two particles. It's all kinetic energy. This thing's going to take what's going to happen is it's going to have a tremendous amount of kinetic energy and then have zero kinetic energy at the closest approach. At the closest approach, it's going to be all potential energy. And that's where they're getting something like this. Initially, this proton has a kinetic energy of 1/2 mv squared. K is K. I use the capital Q and a small q. You call whatever one you want. And you got this. Look, this thing's going to be brought to a dead stop. Why is that? Because it's going to acquire all this potential energy as it races toward the other positively charged particle. The positively charged particle is racing toward the other positively charged particle, and it's being fought. It's like a spring being stretched, only the other way around. It's like a spring being compressed that's able to actually fire back out. You're compressing that spring. Well, at some point, you can't compress it anymore with the energy that you're putting into the thing. This is the amount of energy I can put in to make this thing happen. I can't put in any more. Well, I can't compress it anymore either. All this, it goes from all this kinetic energy to zero kinetic energy when it reaches the point of closest approach. At the point of closest approach, it went from infinity to R. Well, if that was a very, very big number, what's all this divided by a huge number? It's practically zero. So there's a lot going on. You're losing I mean, it's hard to call this thing, to be honest with you. What's the final kinetic energy? You know what I mean? How you want to write? There's so many ways to write this thing. What's the final kinetic energy? The final kinetic energy is 0. The initial kinetic energy is 1/2 mv squared. And there's other ways to write this, but I'm going to stay right here. What do we got? Well, let's just solve for r, basically, is what we're going to do at that point. Multiply by r on each side and divide by 1/2 mv squared. Multiply by r on each side. Multiply by r on each side. Then multiply by 2 on each side to get rid of the half. Then divide by mv squared. It's the end of the story. There's other ways to look at this. There's a number of there's other ways to look, but the mathematics reduces just to this. So let me leave it at this. Two, here's K. Well, here we go. I use K rather than 9. This time I used 8.99, and that's usually what Katz is using. Here's the mass of the proton. Yeah, it's a lot. A lot to be said. Grind out the numbers. We've got 3.83. And here we go. And that's your answer for number 13, you guys. How are you going to look at something like this? Again, there's at least one other way you could look at it. It kind of reduces to the same thing. You're actually getting the difference. You got initial kinetic energy of this much and final kinetic energy the other way. Whereas at the other one, you've got the way they play the whole thing out, you guys, how they're actually doing this whole process. What you're talking about, the potential. And a lot of times there's just a number of things they do here, guys, with this, and to show you that we can look more when we talk in person. Some of the subtlety of what can be said regarding something like this. You could say something to the effect. And I don't want to open this thing up too much like that, but they're saying if you're gonna say, the absolute value of stuff. Let me try to look here. Just don't want to go in that direction. Let me leave it at that, guys. I think this is going to lend itself a lot better if we go toward how they actually do this stuff, how they're actually looking at it. When we actually look in person, you guys, I think we're going to be in a lot better shape when we're doing this. So let me leave it at that. This is the argument. It should be pretty straightforward how you're doing something like that. So those were problems. Those were problems 11, 12, and 13. Let's go to 18. A conducting sphere with radius 0.25 meters has a total charge of 6 millicoulombs. A particle with a charge of negative 2 millicoulombs is initially 0.35 meters from the sphere's center. So it's outside of the sphere because the sphere only got the sphere has only got a 0.25 meter radius, and 0.35 from the sphere's center is where this negative 2 millicoulomb charge is located, at least initially from there, and has moved to a final position of 0.50 meters from the sphere's center. So what's going on here for 18? A and B. What is the difference in electrical potential between the particle's final and initial positions? Delta V equals V sub F minus V sub I. B, what is the change in the system's electric potential energy? So that would be 18. Okay, now how are we going to look at this? And like I said, it gets a little messy how they do stuff. There's so much, there's so many ways to kind of visualize something. It's almost, okay, if you got this thing visualized at some decent level, just leave it at that. And then kind of be able to work with it. So what are they saying here? We're saying basically potential potential is KQ over some R. So if you kind of looked at it, let's see how they want to play this whole thing here, guys. Sometimes you even see, like when they're talking about potential, you see like a negative in front. And if it's a difference between negatives, it's not really an issue. It just, like so many other things, there's a lot of devil in the detail, you guys. So let me just kind of keep it like this, get a gut feeling and say, look, let's talk about a magnitude of a potential at the very least, and not look at all the formalities right now, and just say K is a constant, Q is a constant, oh, no, K is a constant, Q might be able to vary, R might be able to vary. What are we talking about regarding potential? Regarding, potential means something when you can get a potential difference. So how do they relate to one another in terms of a difference of where they are in some three-dimensional space, where R goes off into three-dimensional space? How am I going to actually find this? Between two different equal potential spheres of different size, between two different equal potential spheres of each size, or even imaginary spheres of each size, two different imaginary spheres for our purposes, two different imaginary spheres that are both equal potential and both of different size. If you can just deal with the difference related to a Q and an R, you can get an idea of what the kind of potential difference is going on. You're just doing a subtraction between the two. It's kind of easier done than said, you guys. What it's saying is basically this. A conducting sphere with a radius of 0.25 meters has a total charge of 6 millicoulombs. Okay, good. It's all over its sphere. It's all over the outside of the sphere. It pulls as though it's pulling from its center. A particle with a charge of negative 2 millicoulombs. So the conducting sphere itself has a radius of 0.25 meters, has a total charge of 6 millicoulombs, a particle with a charge of negative 2 millicoulombs is initially 0.35 meters from the sphere's center and is moved to a final position further away than 0.35 meters, you guys. It's moved to 0.50 meters from the sphere's center. What is the potential difference? What is the difference in electrical potential between the particle's final and initial positions? What is the change in the system's electric potential energy? Okay. Like I said, a lot of this stuff is maybe a little easier done than said. You got delta V here. You got VF minus VI. KQ over RF minus KQ over RI. This gut feeling thing I'm trying to show you, I think makes the most sense. That's why I'm doing it. At least that's my motivation for doing it. What's going on here? There's a positive charge conglomeration that we're talking about, and there's a positive charge elsewhere that's getting moved in relation to that positive charge conglomeration that is on the sphere. The closer the two positives get to each other, the bigger the potential. Because when you release them, they fire out. That one is going to fire out. If the sphere is fixed, nailed into space, let's say, and it just doesn't move, it's going to fire out the other one quite violently the closer you get to it. When you get to it, you've really compressed the spring and then it fires out. If you move it further away, you've kind of decompressed the spring. So it's not going to fire out as violently. There's been a change in potential. There is less potential. There's been a drop in potential. Should be a negative answer. Let's see what happens. That's that. So write that up here. Millicoulombs times 10 to the negative third. See, the work that gets done, I mean, it's not going to take work to move it that far. The spring will help you push out from 0.35 to 0.50. That's why you're seeing a negative here. The Q is the initial guy. If you multiply, it'll tell you how much energy has been expended from the system as well. If you multiply by the 2.0 times 10 to the negative 3 microcoulombs, the charge that's actually being moved. Right now I just care about the potential, so I don't have to multiply by that. You're going to end up at 0.50. You started at 0.35. You got the MKS system set up. And there you go. And that, just to clean that up a little bit and kind of make it with the scientific notation, the standard scientific notation, make the magnitude of this 10 times smaller, so you make the magnitude of this 10 times bigger. But there's a drop in potential for that to take place. Same thing as this. I mean, they mean the same thing. It's just written more in the standard scientific notation on that. That is A. That is A. B. What's the change in the potential energy of the system? I've already kind of alluded to that earlier. The delta U is you're going to lose potential energy. Why? Because you're undoing the spring. You're letting the spring uncoil a little bit, controlled all the less, but you're just letting it uncoil a little bit and you're stopping. You went from 0.35 over to 0.50, you let it uncoil. You let it uncoil 15 centimeters, 0.15 meters. 0.5 minus 0.35, you let it uncoil 0.15 centimeters. 0.15 meters or 15 centimeters, in a sense. The E field is kind of the coil at that point, right? And how the potential difference is working. You're just simply doing this. You already just discovered the delta V. Now multiply by that Q I told you about. That Q we were talking about. Let me just see here, guys. Should not have put a negative there, or did I put a negative there? Yeah, there it is. Yeah, that's what it would do. Okay, this is now it gets rather interesting. Okay, let's kind of, so I don't want to like undo much of what I said. If both charge conglomerations, if both charges were positive, everything I just said is true, and I was kind of working under the assumption of a positive charge getting pushed. It's always a positive it's always a positive test charge. It's always a positive test charge that is being the reference point. The positive test charge, how does that work? You know, how would a positive test charge move? Okay, yeah, we said all that. In reference to a positive test charge, you would lose potential. If it was a positive test charge being moved from 0.35 meters to 0.50 meters, you are uncoiling, you're letting the spring uncoil itself. You don't have to do any work on that. The spring's not going to have as much potential energy if you let it uncoil. If it's a positive charge conglomeration on the sphere, and it is, and there's a positive test charge, which I'm making up, that's the way I should have said it earlier. I'm sorry, I'm saying it now. The positive test charge will just get pushed and energy is expended. It doesn't have the same amount of potential energy after you let this situation uncoil. True. That's why you have lower potential. The lower potential is always in reference to a positive test charge. It's always in reference to a positive test charge. True. True. Absolutely true. Yeah, what happens if you do that with a negative test charge? That's another story. With a negative test charge, the negative is attracted to the positive. So if you pull it out from 0.35 meters to 0.50 meters, wait a minute, the negative and the positive, there's an attractive force there. You pull it out, you're stretching a spring that wants to bring you right back. And it's going to show in the mathematics, conveniently. This is negative 2 times 10 to the negative 3. This is negative 4.62 times 10 to the 7. Negative times negative is positive. Yeah, you are increasing the potential energy of the system. If it's a negative particle, why are you increasing the potential energy of the system? You're increasing it because the negative wants to stay where it is. If you got to get the negative away from the positive, you're going to pull it. You just made that spring, you just stretched that spring, and the spring's going to want to come back more violently than before. And the negative times the negative gets you out of the woods, and you do have an increase in potential energy. There's an increase in potential energy of this. There's an increase in potential energy of the system if one's positive and one's negative, and you pull them away from each other. Yeah, it's like me picking up a shot put and going up some experimental facility. Hey, I'm 100 meters in the air. Let me drop it. Well, I just gave it a lot of potential energy. If I climb another tower, not 100 meters tall, but 300 meters tall, no air resistance, same gravitational field and everything, from 300 meters and I drop it, there's even more potential energy. Because there's an attractive force called gravity. Well, this one kind of mimics gravity in a sense. One's positive, one's negative. Yeah, the more you pull that away, the more potential energy you're giving the system. What does that mean? When you let it go, it's going to be going really fast at the very end of the journey compared to if you didn't pull it out so much. If you pulled it out just a little bit, you gave it potential energy. If you pull it out very, very much, and there's a positive and a negative under consideration here, very, very much, there's going to be a great amount of kinetic energy at a certain point that's going to be acquired because there's a lot of potential energy that's going to get released. The negative times the positive got you through the woods on that. Got you out of the woods on that. This answer has to be in reference to what would a positive test charge do? How would a positive test charge behave? Well, yeah, if they're both positive test charges and you're going to go from close to far away, that's a negative answer. You took away, potential energy was dissipated, the spring was uncoiling itself, it lost potential energy for you to bring it to another point. You controlled, in a controlled manner, you brought it over to some other place. Yeah, you did. Well, yeah, that place where it's at doesn't have as much potential energy. And that's where you're getting that here, if they're both positive. If one of them's a positive on the sphere, its center, on the surface of the sphere, conductor, and it goes from the center, it's 6 times 10 to the negative 3 coulombs, 6 times 10 to the 3 coulombs, positive. And if the other one were positive, which is not, but if the other one were positive 2 times 10 to the negative 3 coulombs, that's the behavior. If it was that, there would be a loss. If they were both positive, if that was positive right here, bam, there'd be a loss of that much. That's kind of where I was going. You're always going in reference to a positive test charge. When it's not, throw in the negative number there and you're going to be fine. There's a gain in potential energy. Absolutely. There's a gain in potential energy when I climb the stairs real high at a particular facility and there's a sand pit down there and I throw the shot put off it. The higher I climb, the more potential energy I'm giving the thing. The further away I get. That's if the charges are opposite one another. And that's kind of what happened here. It's very interesting. This is kind of indicative of, there's more to it. I don't want to say any more on that. But this is absolutely the way it is. All right, that's number 18. Let's proceed further. Number 43. Consider a thin rod of total charge, capital Q, and we're assuming positive charge. I mean, you got to make that kind of assumption. I'll try to be pretty straightforward with you guys if I'm asking an exam question like that. But for problem number 43, consider a thin rod of total charge, capital Q, and length, capital L. Show that the electric potential at point capital P, a distance x from the end of the rod, is given by capital V of x equals K capital Q over capital L times the natural logarithm of the ratio x plus L over x. Great question. All right, that's number 43. Okay, so let's see how we'd like to look at this. Again, there's a lot of ways you can look at a lot of things. I've already said that. Sometimes just the gut feeling is the way to go. And if you got your act together, you should be okay. So basically, consider a thin rod. Consider a thin rod of total charge capital Q and length capital L. Show that the electrical potential at point capital P, a distance x from the end of the rod, is given by Vx. So you want to prove, you want to get that the potential is given by this. And again, you're using positive test charges, as I said last time. You're using positive test charges as your comparison, as your measuring stick on how you're doing a lot of this stuff. How would a positive test charge act? They want you to do that. They want you to know that's true. Okay. It's a fascinating conclusion in its own right. I mean, let's get to it. Let's see if that's actually true. Let's see how that works. Well, they're saying that's X. This is, now you can debate how you want to write this, but here is the thin rod of total charge capital Q. The length is capital L. Let's just see here. They want you to consider, that's the distance x. This is the point P. It's the origin. And they want you to just, draw the conclusions that we're going to draw here, guys. Don't know that this is a great idea necessarily, but let me kind of write it like that. And just, hey, just tell me right here, this is the spot. This is the spot we're trying to find. This is the spot we're trying to find. For the potential at that spot. So how are you going to do it? How do you want to look at it? And then problem 54 also utilizes this as well. So I'll probably keep a lot of this. So let's take a look at it. There's a lot there. It's a beautiful conclusion. Let's just see how it actually works, how they're actually getting the answer for that. You're going to look at it. For 43, you're going to say V equals KQ over R. There is a linear, they don't say a lot, but that's okay. We know that it's a uniformly charged rod. Consider a thin, we don't even know that. We're assuming it's consider a thin rod of total charge, capital Q, and length, capital L. We're going to say that it's uniform, use Occam's razor on this one and make the assumption that lambda pertains to a uniformly charged rod of total charge Q and length capital L. At the end of the day, solve for capital Q, or at least express capital Q in terms of lambda and capital L. We also know that for any, we got to assume it's uniformly distributed. If it's uniformly distributed, it's a lot to say. I mean, there's a lot that could potentially be said, I guess you could say. Lambda is the differential amount of charge divided by the differential amount of length. dq over dl is the same as q over l is equal to lambda. Lambda equals Q over L equals lambda, which is dQ over L. If it's uniformly distributed, that's a fact. That works. If that works, multiply by dl on each side. And dq equals lambda dl. Okay, so true. Well, I'll tell you what. I guess we can look at, don't worry about to the left or to the right. The big thing here that's going to help us out is, or perhaps challenge us as well, is everybody's collinear. Everybody's collinear. We're just looking at this right here. In this instance. Well, I'll tell you what. There is a certain amount of charge right here at this tiny sliver right here. There's a certain amount of charge, and I can talk about potential that it is associated with at this point. This charge here associated with potential at this point here. Okay, I want to get out of the way, guys. Make sure I can get on the film here. You may not even be able to see me, but you'll see my hand here at this point. So if there's a small amount of charge here, right here in that sliver, it does something regarding potential right here. Go next to it, a little further away, there's also a potential associated with that sliver. Every one of these slivers I could make here has a little bit of charge, and way over here, all the way to there, way over here, all the way to there, there's potential associated with that as well. Add all of those potentials. Yeah, there's an infinite number of them because they're infinitely small. It's called a calculus problem at this point. So you got this. Let's talk. The potential, let's make, I know, here we go again. They put this letter L, and this capital letter L is a set number. Yeah, but I'm also going to use capital L as a variable. If you've seen me do work in other places on the films, you're kind of going back and forth with, you can kind of call this particular letter a variable. Later on in the big picture, when the final evaluation occurs, you're calling it a constant. You know, at the end, you're saying, well, there was a set length that was talked about here, a set quantity, a set amount. So you can kind of, there's a little bit of fluidity, I guess, on how you can call something. So you can call L a constant. You can also call it a variable if you want to start calling it a variable to start doing some calculus. Here, I'd like to call it a variable because it's dl. And L varies. I could say L right here, the length from here to here is varies. The length here is 0. The length here is 0.001. The length here is 0.002. The length here is 0.003 until I get all the way to here, and the length from here to here is all of that, or the distance rather. I mean, this distance from here to here is 0.001, let's say. From here to here is 0.001 plus 0.001 is 0.002. Here, all the way to there, the length L, capital L, is 0.001 plus 0.001 plus 0.001, that's 0.003. From here all the way to here, that length is capital L. Capital L plus X is the whole length in the big picture. So what's going on here, guys? What is going on here? Well, we're going to set X. If anything gets set as a constant, believe it or not, it's kind of the X. Because from here to here is X. And here is a value of L, a length right here. I don't want to write too much here. Here's a length of L right here. Here's another length of L right here. Here's another length of L if you want to call it a variable. If you want to call it a variable. I know that in the end we're calling capital L a constant. I get that. But that's kind of that's kind of a logic that we can work with and be okay with. Okay, guys, let me just change this battery. Okay, thank you. Sorry about that. So what we have is the logic I'm kind of proposing here when we're doing that. So how you want to do this? Tell you what I'm going to do. I'm going to leave X set in stone. This ain't changing. This guy ain't changing. This guy goes from here, from here, from here, all the way to here, all the way to there. So I'm going to let that vary. So what we got is, I'm going to go take a look. The integral from 0 to capital L. Here I'm treating capital L. Here I'm treating capital L the way they initially gave it to me, as a constant, more or less. K dq over x plus capital L. Now capital L right here is being treated like an actual variable. Because this was capital L here, this was capital L there, that was capital L, this is capital L. So again, please, you see that in mathematics, they do that. That gets done, but be aware of it and have the fluidity of what needs to be done. There it is. Okay, but what does that mean? Yeah, I know, well, it means a lot. It means we know this. It means that dq is lambda dl. Lambda dl, so you got 0 to the constant L. Yeah, I know, now using the variable L. To the constant capital L, now constant capital L, but now we're going to use the variable capital L. Didn't we say that dq was lambda dl? dq was lambda dl. X is constant. Capital L here varies, is a variable, and dl is the integration that's taking place. And then here we kind of switch gears. We say, okay, now evaluate it here. Pretend it's an actual constant. The thing they initially gave to me up here. Here we treat it as a constant, but while we're doing the integration, you guys, we're allowing this capital L to be this short, or that short, a little bit longer, or that short, or this short, etc., etc. From here all the way to there. Yeah. Okay. So if that's the case, deal with it. Get this done. Get that done. Well, to get this done, this is really the whole dynamic of the whole process. When you do it, you're doing this. K is a constant, lambda is a constant. That's the assumption we had to make. We weren't told to explicitly make that assumption, but we used Occam's razor and we did the job. X is a constant. Capital L varies, and it's being integrated with respect to L. This is kind of like, saying that, U is equal to X plus L, du dl, at this, X plus L, du dl is just 1. Du equals dl. and that's the U. True. In that case, you're integrating. You know, I usually don't go this route. If it's already like this, I just go for the antiderivative and I'm done. But du dl is looking like that. We'll talk about it. Du equals dl. This is u at 0. You know, I'm just trying to figure out where what is u? U is equal to x plus L. This would be, if u is equal to x plus L, you got to put u equals x. But this is L equals 0. Yeah, I know. L equals 0 here plus x. That's x. And this is x plus L. It's really what's going on. Well, you know, it's kind of a horse apiece. And once you get to there, do this, you get ln u evaluated between x plus L and x. That's going to be k lambda rather. K lambda times ln x plus L minus ln x. You didn't have to get quote unquote fancy with this whole thing to get to here. You're still not quite done in the formal sense, or at least in a more convenient sense. But to get to here, you know, you didn't really have to go. You could have played it here and just gone antiderivatives and gotten ln x plus L. You know, plug in ln x plus L, plug in, you know, you could have just gotten the antiderivative right here of this whole thing, and it would have been ln x plus L, right, but you're evaluating that with capital L at 0, which just gives you ln x, and you're evaluating it at capital L being capital L, which would be simply ln the quantity x plus L minus ln x. It's the same thing, guys. It's the same thing. You might want to jump the gun and just get to here. This is a pretty easy one to do, looking at where the antiderivatives are and stuff, and to get this all under control. All right, well, what does that mean? That means at the end of the day, you guys, that this is k lambda, a constant. The difference between two logarithms is the logarithm of the quotient. So what we end up getting here, guys, well, I mean, there's a lot of arguments you can make here, guys, but there's the V. V equals all that. Right, I agree. That's what they were asking you to prove, and we just did it. Fascinating problem. Really neat problem. Okay, that was 43. Let's go to 54. It's a very similar, let me not erase too much of this, guys. Save myself a little bit of time, save you a little bit of time too, having to watch it. For 54, according to problem, here's problem number 54. According to problem 43, the electric potential at P, a distance x from the end of the rod, is given by, well, we wrote it all over the place. Right there is what we initially wrote, and that's the answer. V of x equals K capital Q over capital L. Those are constants. They're treated as constants at this point. And they're also treated as constants right here as well. The x and the capital L, also treated as constants. Capital V of x equals K capital Q over capital L times the natural logarithm of the quotient kx plus L over x.
Well, okay. I mean, fine. I believe it. We believe it. Use this equation to find the electric field at a distance x from the end of the charged rod.
Let's find, now we found this. We found the potential. Now tell me what the electric field is. We assume this is a positive charge. This is a positive charge. This is positively charged here. The test charge is right here. So the E field, if this is positively charged and this in aggregate is also positively charged, positive, repulsive force, this thing is nailed in right here. It's not going to move. A positive test charge here will go in the negative direction. I'm going to get a negative answer here. How do you want to do this? Well, we know a lot of stuff here. It's a whole lot you can say. There really is. So let's take a look at it. Let's leave some of this up here. And let me see. Don't want to erase too much of this. Yeah, I think we're fine. We can discuss this a little bit. Okay, so let me. There's a lot you can keep, a lot you can take away, I guess. Let me leave some of this up here, and some of this is going to go. So again, the conclusion we got here is quite good. On the mark completely, guys, and we're good. We got this. For 54, let's take a look at it. 54 pertains directly to what we did in problem 43. So let me kind of just leave it up there, all the stuff we had said. And okay, let me leave this up here. There might be some cause for further discussion. We'll see. We'll see how things proceed. I mean, there's a number of ways to go here. Just trying to mess a little bit. There's just some other. I'm trying to think sort of outside of the box of what I actually have in my notes here, you guys, and I think that's not a bad idea sometimes, but sometimes it's an invitation to some more issues possibly. So let's see what we can say here regarding this stuff. How they talk about potential, how it all works. They basically a whole lot you can say here, guys. I just want to argue with myself a little bit on this. It's going to be a little bit outside of the notes of what I did here, and then I'll definitely get back into the notes as well when we do it. Use this equation to find the electric field at distance x from the rod. So a lot of arguments can be made here. Let me kind of go. Let me kind of go the hard way toward this, and then let me show you the easy way as well. I hope so. Yeah, I hope it's relatively easy to look at when we do it. How do you do stuff like this? What is this stuff? How does it all work? You could say this, guys. Look at the same exact setup here, And if you were trying to find the E field, let's put a positive test charge here, and let's find an E field here. Let's find an E field here. Well, wait a minute. If this is a positively charged particle, or if this is all positively charged particles, and this is positively charged, there's repulsion, and it goes in the negative direction. True. So how do you want to look at it? So if any way you do the integral here, I can't go into all the detail on this, but I'll say something. I'll say that delta V is negative R initial to R final E vector dot dr vector. Notice why I've made a big deal out of the dot product and the cross product, and even when we talk about deriving them, I try to look at something and say, hey, look, we got a derivation of this as well. This stuff's pretty serious business. You could say something like this, they got a negative right there. Does this make any sense? Well, yeah, I believe it does. Definitely makes some sense. Yeah, true, but let's find the E field first. Well, I already said it's going to be a negative. It's going to be a negative. It's a positive potential because it wants to fire it somehow. You're not losing potential, I mean, in a sense here, but let's talk about the E field. What's going on here? How would you do this? It fires it. Talk about magnitude. Tell you what I'm going to do. Isn't the E field KQ over R squared the general look of the E field? Yeah, it is. Let's use calculus to do a lot of this stuff, taking the same kind of big walk to find out what's going on over there for an E field. This is maybe easier done than said. The E field is K dq integrated. Yeah, from where to where? Well, like I said, there's this thing about positive, negative. Be careful. Don't worry about the location as much as far as just finding out where you're going to go. You're going to go from 0. You're going to go from L equals 0 to L equals L. The X is already present. Look, let's talk. Before I even do limits of integration here. Do we have, how about lambda dq? Forgive me. How about lambda dl gives me the dq? Lambda dl gives me the dq. The distance under consideration, and I don't want to get into all the possible. We can lose sight of the forest because of all the trees, and I'm the guy putting up all the trees sometimes. So let's just look at this. Let's set it up. Let's see what we can say about an E field. And then I want to kind of ask some questions about that E field that we just discovered. Okay. K lambda dl, you're going from K lambda dl, and then R squared is the bottom thing. What is this thing? It's going from X to X plus capital L for what's going on here. So this can get a little on the touchy side. How do you want to talk about this L thing, man? I'd almost want to call it something else. I could call it an X. I could call it an X and then get a DX. I'd call it an L and call it a DL. It's almost more convenient to start from 0 and go all the way to X plus capital L. Capital L, X. 0 all the way to x plus capital L, and then you're starting, and then at that point that'd be your R. Interesting. Maybe perhaps that's some way to go there. You know, perhaps that is some way to go there. Then you got to worry about the you know, x, the DL. I think I don't want to throw the dice on that one. I know that we can do it, but like I said, being that I'm doing this cold right now, guys, I do not want to get into a 20 or 30 minute adventure on the whole process. I mean, it's a long process as is. Let's just tell you what. Let's still take a look. Let's go from x. We could do the L's on there too. Let me see here. Let me work with the L's. Let's go from L equals 0 to L equals capital L. And let's go K. There's so many ways to do this, guys. You kind of see where I'm going. That's lambda DL. L equals 0. What's the difference at L equals 0? What's the length at L equals 0? It's x. What's the length at L equals L? It's L plus x. So be careful. It's L and L plus x. So you're going from 0 to L, and what you're doing is it's going from x to x plus L, so you got to write it like this. The total distance, this is the radius. It's so tempting to write R and do integration with R, and we can do it. I'm a little apprehensive about trying to do that cold right now. And we got this right here. This tells you the E field. Yeah, it's going in the negative direction. I don't want to, it seems like I'm taking a kind of a cheap shot at this thing. There's more. The magnitudes are going to be fine. You just got to look out for what's going on with the E field. The E field's pushing it this way. It's pushing it away if they're both positive. It's going in the negative direction. So that makes sense. So it's saying what it's saying is it would have the tendency at this point for there to be to go to this point, it would do a positive amount of work, or you'd have to do a positive amount of work to get it to go. To get it to go to the right, you'd have to do a positive amount of work to get it to go there, so you get a positive answer here. The E field is fighting this way the whole time. So we're going to say it's negative. Maybe this gives you a gut feeling for what the heck's going on. That is E equals negative K lambda integral from 0 to L dl over the quantity x plus lambda. Now look, be careful. The L is a constant. The L is not a constant. It's a constant here, but not here. It's a variable here. It's being integrated with respect to L. The x is a constant. When you get the antiderivative of all that, you end up getting negative K lambda. This thing right here, it's the quantity, you know, remember we said that the DL and the DU are equal. If you set U equal to, if you were to set, U equal to X plus capital L, U equals X plus capital L, DU is the same as DL. If you want to play the game here, guys, you're integrating you're integrating with respect to U of, you know, you're going U to the negative 2 du, which is, you add 1 to it, it's U to the negative 1, and then you go 1 over negative 1, which is negative 1. It becomes negative 1. It becomes negative 1, this whole song and dance, to the 1 power. Evaluated between 0 and L. There's other ways you can do this. I think they're really good. I just don't want to get into too big of an adventure when I'm on film with this thing. I'm trying to do it kind of cold as is. It's absolutely doable. It just let's stay with this. We got to the dance driving this car. We're fine. That setup. Let's just stay with that setup. It's not the only setup, and there's other ways to do it that are just very good as well. What's negative 1 times negative k lambda? So that would have, yeah, let's just stay with it. We've got this. We got negative 1 times negative k lambda over x plus L, evaluated between L and 0, which is the same. So that's the look between 0 and L. Let's go. Put the L right here. That's x plus L. So we got a k lambda right here. Put the L right here. We got 1 over x plus L. That's a relatively big number compared to putting a 0 right here. You're plugging in right for the L. Constant here, variable here, constant here. Sorry, but that's the way you see it written a lot of times. Here's a constant, here's a variable. Put the constant into this variable, x plus L. You got it. Got the constant. Put a 0 right here. This is big on the bottom. This is small on the bottom. Small on the bottom is a bigger number than, with small on the bottom, 1 divided by small is bigger than 1 divided by big. This is a negative answer. Hey, that's consistent. That thing points to the left. Negative values. Okay? You're probably wondering, okay, what is he doing? Okay. Well, I got that for the E. This is very important. We got this. Yeah, that's true. Is there a way to simplify that a little bit? E equals k lambda times the quantity, this. Yeah, true. Now what? What do you say you multiply by a special 1 here called x over x? And, multiply by a special 1 here. Get a common denominator. Let's see if we can make this thing look like something. Multiply by a special 1 here. This guy right here, just this guy. Multiply by the special 1 called x over x. It becomes x over the quantity. Multiply by the special 1 x over x here, and it becomes x over the product, x times the quantity, x plus L. And multiply by a special 1 here of the quantity x plus L over the quantity x plus L, and that becomes the quantity x plus L over the product, x times the quantity x plus L. So you get common denominators there and stuff. Once you got a common denominator, you got the x over here, you got the quantity x plus L over here, x minus x plus L, so it's looking like this. Once you do all that, k lambda, that's what E is. Yeah, certainly true. X minus the quantity x plus L is negative L. And you got all this business on the bottom. Negative L Yeah, it's interesting. Okay, according to the setup, yeah, it's completely consistent too. So you got something looking like this. So what is going on here? I mean, this is fine. I mean, this is good. So at the end of the day, there it is. Yeah, there it is. That's what it is. So great. Let's see what we can. Now we did this just by definition of what's going on. You know, what the heck does all that mean? I mean, it means this. If you were going in the negative x direction, if you had your positive test charge here, you had a positive test charge here, this is all more or less positive, it's basically positive. The conglomerate is positive net, some net positive, and here's positive. If you were going this way and pushing this thing, you're going in the negative direction. You know, you'd be doing an integral. These are negative values, but the e is a negative value. You multiply the two, you got positive work being done. If you went here, you'd have to. There'd be this thing's doing positive work if it pushes you that way. It's doing negative work if you're trying to force this charge to get close to this charged conglomeration that is nailed in somewhere. It can't move anywhere. So it's doing negative work. So that would be, it'd be positive distance here and then negative. So yeah, it's consistent. The bookkeeping can get a little aggravating, guys. The absolute values are what they should be. Now you just got to get what, if it's positive or negative a lot of times. Okay. Just wanted to say that. Well, for the record, we just did say it. And then when we look at it,
For 54, use this equation to find the electric field at a distance x from the charged rod.
Well, I didn't cheat. I'm about to do it now. We know with this in mind here, if this is true, the E field, you multiply by a negative, the dot product, it gets a little interesting, I guess you could say. You'll get the E, if you take the derivative here with respect to R, and the derivative here with respect to R, you got negative E vector equals negative dV dr. You got negative E vector equals dV dr, multiply by negative 1 on each side, E vector equals negative dV dr. That's kind of the argument. All right, so let's see what we can say regarding this, you guys. The way this whole thing proceeds, if you were going to take the derivative with respect to, you'd have the vector. Let me just talk about this for a second. Yeah, there's a number of ways you could do this. Let's not say much more than that right now. You got this right here. From this, you guys generally know that if you take the derivative of an integral, you're getting basically the item that was being integrated, and here you're just getting the derivative of what was there. So basically they're saying that E vector is going to equal
negative dv dr, some association with the r hat. I didn't put the r hat in the notes, but that's kind of the argument here, guys. Well, yeah, the r hat under consideration, we know it's associated with the x direction. It's going to be negative dv dx associated with the x direction. It's going to be negative d, what do we say v was? We discovered v to be this, kq over L, lambda, the whole thing here. So, forgive me, guys. There's one more thing to say here. What the heck is lambda? What the heck is lambda? Isn't lambda's dq dl. Lambda's dq dl, but lambda is also q over L. That's q over L. So you can write it as Q over L is lambda. It was there. Okay, that's fine. Let's stay with that. I'm going to try to stay consistent with it. Let's prove it. You saw me go old school and get this answer old school, so to speak. We went right from the beginning. We went right here, and that got us. We did the work, and it got us all the way over to there. Now take constant, constant, constant. Oh, yeah, these are constants. These are constants for this instance. And then this is going to be like a variable. This gets, so it's now it gets kind of rough, but that's a constant. Leave it. That's a variable. Deal with it. So kq over, maybe it's better to leave the lambda there, is what I'm trying to say sometimes. Maybe I could have left the lambda there. Could have and should have. I don't know. Who knows? Go dv dx. Go negative dv dx to get e. That's kq over L. Treat that like a constant. Why? Because q over L is a constant. Q over L is a constant, so treat it like a constant. ln true. Yeah, that's true. So let's go. Let's write it as, do you mind? I mean, there's so many ways to go, guys. I hate to do it to you. The negative right here, you can bring it to the inside. So the negative right here, you can bring it right here and make it negative the quantity kq over L. Or you can move the negative all the way to here and make it negative all this, and there's no negative at that point. What's so big about that? Well, negative ln this quantity is the same as positive ln the reciprocal from the laws of logarithms. True. Once again, somebody could say, so what? Okay, true, what? So big deal. Well, we just said that all this, so you come up here, I guess, to get the E. It's going to be equal to that E also, actually, but let's stay here. Bam, bring the E over here. Come up here, go there. What do you got? You got KQ over capital L. DL, then get that out of there. It's a constant, so you can get that out of there. And it's DLN, the ratio x over x plus L dx. Yeah, great. So what? Well, yeah, then that's this. Then it's just simply this. And it's d ln of this. Ln, the logarithm of a ratio is the difference of the logarithms. Dx. That's KQ over L. By the sum rule, take D, by the sum, this minus here, this minus here is the same as plus a negative. We'll do the sum rule. D ln x dx is 1 over x plus D ln of all this is 1 over x plus L, and that's a negative. All right, well, I almost didn't need to do it. Plus a negative is the same as minus. What are we looking at, ladies and gentlemen? KQ over L, 1 over x minus 1 over x plus L. True. Well, what is that? We've already seen this. It should look familiar. I know I had a lambda there. I mean, when you saw me do it, the Q over L, the capital Q over the capital L was lambda. It was K lambda. And this business was special 1. Well, I had something similar to this at least. It was special. Here it'd be special 1, the quantity x plus L over the quantity x plus L. So it becomes x plus L over the product x times the quantity x plus L. Here, special 1 x over x. Multiply it, you got x over the product x times the quantity x plus L. The x times the quantity x plus L is the same on the bottom. Here you got x plus L. Here you got x. Do the subtraction, you got L left over. Wait a minute. Right. Well, yeah. At the end of the day, you got L left over. You got this. Sure, that's true. What am I talking about? Isn't there more news here, guys? Yeah. All this is true. What I did with the lambda was fine. What I did with the L was fine. How about that? Yeah. At the end of the day, it's going to be that. If you really want to do it, let's see what we got. We got the E going negative KQ. See, we didn't catch it the first time. I didn't catch it the first time because this was lambda. Capital Q over capital L. Capital Q over capital L is lambda. That's fine. It stays. It works. No big deal. It's a horse apiece in a lot of regards. I mean, so you look at this and you've got, I think this breaks down about as far as it does now, guys. Finally, after about three looks at it, all 3 looks were correct. There's nothing wrong with it. The best is the one that's reduced, and that's what we just did. We saw it, we fought through it, we got it. Is that true? Well, that's what we're claiming. When you did the derivative, ladies and gentlemen, when you did the derivative of the E function, you did get this, which, by the way, was identical to all this in its different manifestations. It was the same as negative K lambda times capital L over the product x times the quantity x plus L. The lambda was Q over capital L. Negative K capital Q over L times capital L over the product x times the quantity x plus capital L. That works. What am I thinking? Throw that out of there. That's the best. Well, that's when you did all the derivatives. Yeah, let's get this straight, guys. When we did this, we got this for a final answer. We got this for a final answer when we did the derivative. When we did the derivative of, I mean, in the way they tell us to do it, right? When we did this, we got all this. That was by getting the derivative of the v function. The derivative of the v function with respect to x was all this, all the way up here, came down here and got us this, which is equal to this. Great. It is equal to this. And how, was there another way we got this? Sure. We did the integral. We integrated all the dE's and got this exact same answer, which is this. We obtained this answer by integrating the dE's. And we got that answer. We also obtained this answer by taking the derivative of the v function. This guy right here got us that answer. So did the integral with respect to e got us that answer. Sorry it's that long-winded, guys, but that's what happened. Let's see where, and there it is. You're looking right at it. E sub x is k capital Q over, E sub x is k capital Q over the quantity x times the quantity x plus L. And that's it. That's it. Okay. Problem number 69. What is the work required? Problem number 69. What is the work required to charge a spherical shell of radius r equals 43 centimeters to a total charge of 67.0 microcoulombs with charges that are brought to the shell from infinity? Now, again, Occam's razor again here, guys. And I'll tell, is the thing completely uncharged to begin with? I think it is. I mean, that's probably the realistic way to look at it. For problem number 69, what is the work required to charge a spherical shell of radius r equals 43 centimeters to a total charge of 67.0 microcoulombs with charges that are brought to the shell from infinity? The more you put charges on the shell, those positive charges are going to fight that you're going to bring other positive charges in. There's going to be a repulsive force. So you got to put a lot of energy into doing all this. So let's take a look at it. Okay, I mean, initially it's very easy. Even though it's from infinity, it's very easy to bring charges onto an empty shell. To bring positive charges onto an empty shell. It's very easy. Yeah, there's let's just say nothing else is going on anywhere near where you are where this is happening. There's like just, let's say there's like a sector here where we're just not, there's nothing really going on. There's nothing else around for our purposes. That's the only thing going on at that point that's going to have any significant, that's going to have any effect on what we're doing. Well, initially bringing charges from negative and bringing charges from infinity
Initially, it's no work at all to get to get a charge there. After that, that charge that is on that sphere is going to fight what's going on, is going to fight what's coming over. And the more charges you get on the sphere, the more of a fight there's going to be. All right, well, let's see how this plays out. I mean, I think the mathematics reflects this reality in a very simple manner, in a sense. V equals KQ over R. Work is going to equal Q times V, or delta V, depends where, how the stuff gets, how you want to talk about it. The potential difference that you're trying to overcome. We said those, in prior discussions, there's ways you can look at it. Well, there you go. There's the work you got to do. What's going on here? Yeah, it's a pretty fascinating matter in its own right. I mean, guys, isn't work equal to, there's a lot of ways to go here. Isn't work the same as force times distance from, and you got it, like if you're coming from far away, you want to throw a negative in front of this thing so you're guaranteed a positive answer to get the work when doing a positive test charge going on to something positive. So you're going from R initial, which is at infinity, and RF, which is a certain distance away from there. So they throw a negative on there. We've seen this. Let me kind of write this a little bit better, guys. Don't want to. We've been down this path, guys. But let's talk a little bit. From an initial, which is very far away, and you're going in the negative direction, so to speak. So go the opposite of negative. So that's possibly a good justification, at least to remember what's going on. You're doing something like this. Well, we know that the force, again, we got the limits, okay. Q times E, say it's a positive charge, moving in a negative direction. There's an E field, you're fighting an E field, and you're going in a direction opposite the E field. So when you do a dot product here, you're going opposite the E field is 180 degrees. The dot product of two vectors at 180 degrees from one another is the magnitude of both multiplied together times -1. -1 times -1 is a positive answer. So that's where the positive amount of work comes forward when you're doing something like this. So let's go. I mean, you're talking about this. Let's write it like that. Let's say they're completely in line with one another. They're collinear. They're just 180 degrees apart when we're doing this thing. You're doing this. Let's not worry a whole lot on that. Let's just do this. Let's get the magnitude. Let's pretend we're going from one to the other a far distance away, and we're just going to deal with the magnitude on this. We'll kind of figure this out. You know what? Let me still stay with that actually. E is K big Q over R squared times a little q. Put them right here. dr. Say Q is a real small charge. So what you're doing is and you try, now you got to be extremely careful with this whole process. The E field varies. you're kind of, and where the Q is going to be. So, I mean, you can find out. Yeah, there's a lot more to it than means. Yeah, the Q, guys, is going to vary. The E field itself is going to vary. It's going to be essentially not just the Q. It's going to be. So if you looked at it, the E field itself, it would be Q, and the E field would be dq r squared. Integral here it's this right here that's going on here, guys. The issue is, what are we talking about for? So you got an E field, how that works out, and then you're always, so I guess you'd have to find, in terms of what the potential would be, what's the work equal to? Yeah, it's a little crazy. I mean, this would be basically however much charge you got on there is Q, and how the E field varies, you got the dq on there. Let me kind of take a little snapshot of this. The E field is going to vary because Q is going to keep increasing to a certain point. That's the E field you fight. If you multiply by dq for that distance, yeah, this is it. You multiply by d, and dq is always increasing. You're integrating this, and this is actually your E field. The E field under consideration is, where are you in relation to where something's coming? And this R is actually the surface. The surface of the surface of the thing. So it's being brought in from far away. There's nothing wrong with this, but it's not really necessarily what's happening as we proceed, as the R proceeds. We can look at it and see that. You can look at it and you say, okay, well, you got this. Again, guys, I'm doing this completely cold to try to figure out. There's got to be a way that you can look at this when you say this, and so let's see what we have here. So that's all completely true. It's already accounted for in the sense that there is the E field that has to be overcome over a particular distance, and I guess we could figure out. There's certainly a lot that comes to mind on this whole process, you guys. I mean, this is certainly what I was trying to do. If I was going to say the E field, though, let me just kind of look at the E field. Force dr, and the force varies. The force varies with respect to r and with respect to q. So you've got the QR amount. So what you got to do is basically, you could do a lot here. You could say, and this is not how I got, don't worry about this, guys. I mean, don't worry about any of this as I'm doing this on my own right here. How this is going to play out. don't worry how this is going to play out as far, because there's another way to look at it. But you could look at it and say, well, how much work is required to bring a test charge from a particular point? Any test charge. So I guess what you could say the V is in terms of magnitude, you could say for any particular amount of charge, Q, and let's set it constant. Let's for right now set it constant. You got R squared here, and you're gonna do this integral. How much potential is there to bring it from infinity, some very big number, a very big initial number, to a final number of, let me call it R. RF is going to be R. RF is going to be your R. Let's put it that way. And I'm going from a very big value to a small value. I got to do work there against an E field. How much work gets done? Well, the way it's getting integrated, it's going to be negative and then a negative again. You should be fine. This right here ends up coming out to negative kx over r from a very big number. Let me write down infinity. It's not the most rigorous way to say it. And this guy right here, this is R. Let's see exactly what we would say here. I guess you could do a whole bunch of things. You could have it go from the R to the RI, or from the RI to this. The way this works out is correct. You got R, you got this. Sure, if you did the the magnitude is the same in either instance. Let me leave it this way. So what amount of work would you do, potential speaking wise? Again, guys, the magnitude kind of wins the day on this whole thing. You've got a delta V there, or a V, delta V, use them simultaneously. For any particular situation, you got this. Right? And if you want to find the work, so for the E field, you got this. There's really so much can be said on this. What is the actual average E field on something like this? I mean, there's a lot more we could say, guys. Perhaps we can save that for an in-person discussion, possibly, or some other discussion. But you're looking at this. If you've got, and that's the thing. And if we know that work. And let's not worry about negative or positive right now, guys. Let's not worry about negative or positive. Let's assume a positive number. This is the amount of work per unit charge times Q. That'll get you W. And that, yeah, that's true. But, maybe it's better. dQ gives you dW. Why don't you do an integral there? Well, yeah, that's pretty fascinating stuff. The work is going to be some sort of integral with all the dW's taken into account. And the charges are being added onto this as you're bringing more charges to it. To make a long story short, this is K, some amount of Q of charge present. It varies. Initially, this Q is equal to 0, and it reaches the capital Q level at some point. But this is the potential at one instance for the charge. So if you bring a little bit of charge from here, a little bit of charge through this potential, yeah, that's the work you did, and then you got to do it again. Now you've added charge to this, and it's a bigger potential, so there's more work required. And that's where this comes in. And that's kind of what I was
in a very awkward manner trying to bring forward here. I should just come right back to this. So we got this. As you do this, as far as magnitudes are concerned, when you actually do something like this, you're getting 1/2. Well, that's a great question in its own right now. Now, what are you doing? You're dealing with from infinity to r. So I already took care of the r. The r here is now a constant. It's the radius of the sphere is what the r is. The other business is what makes it all happen, and that's k. KQ squared so 1/2 KQ squared over R, and that's it. And that was, I could have done, all of this is essentially true. It's just got to be set up the right way. Watch out for the signs. My own personal experience has told me that the way to deal with the signs probably most effectively is look directly as to what's being done. If you're from far away bringing a positive charge to a whole bunch of positive charges, you have to fight the whole way. What does that mean? Well, that means the work required to do that is a positive amount of work. If you're trying to bring a negative charge to a positive charge conglomeration, it's very easy. Just let it go and it'll do it itself. You got to actually hold it back. You got to do negative work, kind of just to bring it there. It's not going to be an issue. It wants to go there. So, all right. So you saw what I did there. You got this answer, and that's all you're doing, guys. I mean, the whole process was, if you got this, the v is a function not of distance, because you took the E field and you actually proved, you took the E field and you integrated and you proved what V was for that particular distance under consideration. So this R in this instance is a constant. It's the radius of the sphere under consideration. So you're basically just, like you said, what did we do here? We're getting W is the integral of all, and I'm not going to worry about signs or limits or anything right now. We'll talk about that when we have to. The big thing is it's Q, it's dQ for a particular V with the function. So it's the V function, and the V function changes. The more charges you put on the sphere, the greater the potential is at that location. And you've got to overcome that potential. You got to fight your way through it, and it gets harder and harder to fight your way through it when you're doing something like this. So you got this dq. And it's going to come out to kq, and q is variable. Q equals 0 in the beginning, and it equals some other q. You want to call it capital Q? Yeah, it's going to fill up. In my notes, I got it at small q. I kind of been doing it the same way. How I go back and forth with variables and constants. Right now, let me not do that. The q goes from nothing on the sphere all the way to a full sphere. R doesn't change. And when we integrated the E field, we got the potential. When we did all this business, we were essentially integrating the E field. Well, what was that? Well, it was, whatever it happens to be for a certain charge. Now the charge is constant. That's where the whole thing's wacky. That's what's messing me up. We did this whole thing here. We did it in such a way, we ended up getting negative KQ over R. In terms of absolute value, it's KQ over R. That's not something we're going to worry about right now. We know the magnitude is KQ over R. R was varying, but at the end, you do the limits of integration like I did from infinity to R, then R becomes a constant. Now you're going to start using the problem this way. R was varying. Once you did the limits of integration, and everything. And once you evaluated between the limits, R was a set value from infinity to R. Great. For a given Q. Great. Yeah, that given Q is going to change. So leave the R alone and put a different Q continuously present. Now integrate with respect to Q. Complicated. It's a little, and at the end of the day, how you end up doing it, you end up going, that right there, what does it lend itself to? It lends itself to what you know how to do. Right, evaluate it from 0 to capital Q. I mean, I left it like this. I left it just like this at the end of it. I put it to small q. Doesn't matter. A lot of this stuff doesn't matter, guys. As long the symbolism's not the big deal. Get the magnitudes. Be correct vis-a-vis the magnitudes, and there should be a lot of functionality to the whole thing. And there I just wrote the same thing. Sorry about that. So when you do all that, stuff's easier done than said sometimes, that's for sure. It's a horse apiece, guys, when we're doing that. That's the work required. So plug in the numbers. A half is a half. K is 8.99 times 10 to the 9th. Q is 67 microcoulombs. That's 67 times 10 to the negative 6 squared. You want to put it right on the sphere. You brought it from infinity all the way to 43 centimeters from the center of the sphere to put it on the sphere. 43 centimeters from the center of the sphere, is 0.43. That's the half. This is 0.43 meters. So a half times 8.99 times 10 to the 9th times 67 times 10 to the negative 6, that whole quantity, 67 times 10 to the negative 6 squared, over 0.43 meters. And at the end of that day, how much work did I get done? A lot of work. I mean, at the end of all that, and that's problem number 69. All right. Problem number 78 is pretty fascinating also, I think. Problem number 78, an infinite number of charges with Q equals 2 microcoulombs are placed. So each one is 2 microcoulombs, apparently, right? An infinite number of charges with Q, each Q being 2 microcoulombs, are placed along the x-axis at x equals 1 meter, x equals 2 meters, x equals 4 meters, x equals 8 meters, and so on, as shown in the figure. Determine the electric potential at the point x equals 0. These are positive charges. Determine the electric potential at the point x equals 0 due to this set of charges. Use this. Let's kind of see what I could say here, guys. Use the mathematical formula for a geometric series. Okay, this is interesting. We're seeing some patterns here. Let's get to it. What's going on here, guys? We're seeing some kind of pattern here. They gave us a hint, and the hint makes a lot of sense. Okay, what's going on here, guys? I mean, it's pretty easy stuff. It's a lot easier than you think it is, basically. They're telling us that every one of these infinite number of charges, the answer should be infinite. Not so fast. The distances are increasing also. 2 microcoulombs is 2 times 10 to the negative 6. Right. I mean, so it's 2 microcoulombs, and they're placed on the x-axis, and the way they're doing it. And they want to know determine the electric potential at x equals 0. It's that simple. Here it is. Here's 0, and they want to know what the electric potential is. And this thing goes out toward infinity. Here is location 1. Here is location 2. Here's location double, wait a minute, here's location 1, and if you double 1, you get 2. If you double 2, you get the third location, which is location 4. If you double 4, you get the fourth location, which is 8 after you double 4. So here's 1, double the distance 1, and you get 2. Double the distance 2, and you get 4. Double the distance 4, and you get 8, assuming I knew how to draw this thing, right? And they're saying just keep going. What's going on here? Well, there's absolutely a pattern here. There's absolutely a pattern here. So let's take a look at how we're going to do it. How are you going to do this pattern? How are you going to look at this whole process? Well, look, there's a lot of them. There's an infinite number of them, actually, and I want to find the potential over here. Here's a distance of 1. Here's a distance of 2. Here's a distance of double this right here, which is 2. Here's a distance of 4. So here's 1. Double 1, you get the distance of 2. Double 2, you get the distance of 4. Double 4, you get the distance of 8. I'm not saying it's not exactly the greatest scale, you guys, but I think you know where I'm going. So on and so forth. What's going on here? Yeah, there's Q's everywhere. It's the same Q on the whole process. Q here, Q here, Q here, Q here. A number of ways to go here. Well, let's try to make it easy. Here's V. V is going to be KQ over R, which is 1, plus the other one, also a Q over R, which is 2, plus the other one, which is KQ over R, which is 4, plus the other one, KQ over R, which is 8. We have got to see a pattern here. It's going on forever too, huh? Yeah, it's a geometric series. This is 1. If you double 1, you get 2. If you double 2, you get 4. If you double 4, you get 8. If you double 8, you get 16. If you double 16, you got 32. If you double 32, you got 64. If you double 64, you got 128. If you double 128, you got 256. You get the picture. What's going on here? Well, I don't know. There's got to be an easy way to look at this. How about 1 over 1 plus 1 over 2? Just factor it out. Factor the KQ out of there. This goes on forever. Okay, I'm with you. It goes on forever. This is a geometric series. The ratio is a half. Absolutely. The ratio is a half. What does that mean? Well, it means this. If R is a half, I got a question for you. What's a half to the 0 power? What's a half to the 1 power? What's a half to the 2 power? What's a half to the 3 power? Yeah, that's everybody else. Wait a minute. That's 1/8. If you cube this, it's 1/8. Square this, it's 1/4. This is a half. This is 1. This becomes 1 plus a half plus a fourth plus an eighth. Yeah, sure does. Sure does. Something going on here. Yeah, absolutely there's something going on here. What you're looking at is if there's a formula for this, and the formula for this is when it's looking something like this, and it's looking like this, for example, this right here in the limit, this whole thing in the limit becomes, there's a lot of ways, I'm not sure if I want to prove this just yet to you guys. If you were to do this, you are going to get you're going to get 1 minus a half to something huge, which is just 1, and this is just 1 minus r. When the numbers are less than 1, that's the sum. Yeah. Great. What does that equal? Believe it or not, all this, if you go a full meter, and then you go half a meter, and then you go half of half a meter, you go a quarter meter, you go half a quarter meter, you do it. If you add all these up, you're not quite going to ever make it to 2, but you're going to get really close to it. This right here, half the race, a quarter of the race, an eighth of the race, and keep adding. This right here adds up to 1. 1 and 1 is 2. It's going to come out to 2. And that's what we got here. Didn't we say R was a half? The ratio involved in the summation of a geometric series, called geometric series, there's your answer. 1 minus, even though there's an infinite amount of these, there's going to be convergence. This is 1 over 1 minus r. 1 over the quantity 1 minus r. That's 1 over the quantity 1 minus r. R is a half. 1 minus a half is a half. Absolutely. All those, remember I told you, the 1 plus a half plus a fourth plus an eighth plus ... In the limit to infinity, it's going to equal 2. It's going to equal 2. That right there is going to equal 2. All of this equals 2. All of this equals 2. 2 times kq. And I got a proof of the geometric series. There's an actual in the actual notes. There's a proof of how that would play out, how that actually comes out to be. What you do is with something like this, you say that the sum on something with a geometric series, if there's like a 1 already present, and then to the 0. You got 1 plus all these right here. The way I'll just quickly do it. But it is in the notes. If you've got 1 which is r to the 0. R to the 0 is 1. R to the 0, if that's a half to the 0 is 1. So half to the 0 is 1. A half to the 1 is a half. So that's just r to the 1 plus r to the 2 plus r to the 3 plus r to the 4 plus dot, 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 plus, let's say r to the n. That's a lot. Let's say it's not infinity yet, but I'll say that's all of them. Well, that whole thing is the summation of n terms. If you multiply this guy by r, this is the way the classic proof that they give, multiply this guy by r, you're multiplying all these guys by r, well, what happens? Well, that 1 becomes an r to the 1. There's no more 1 here, right? There's no more 1 here. No more 1 here, but there's an r to the 1. If you multiply this guy by r, it's r to the 1. Multiply this guy by r, it's r to the 2. Wow. Well, you get ahead of the ball game, I guess you could say. You got all these, plus dot, 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 plus you got the r to the n, but yeah, there was 1 extra. Remember, you multiplied it by r, you got that. If you take this and subtract that from it, you got 1 minus r times s sub n. If you take this whole mess, and it can be very, very long, much of it here, and then take this whole mess, take this, take all of this, and subtract all of that, all of these go. R1 minus R1, R2 minus R2, R3 minus R3, R4 minus R4, Rn minus Rn, that's the only guy that remains, and you had a 1 up here. You got 1 minus r to the n. Divide by 1 minus r on each side. Guaranteed answer. 1 minus r to the n over 1 minus r. Now what's going on? If r is a number less than 1 and n goes to infinity, any small number, any number smaller than 1 exponentiated toward infinity goes toward 0. So in the limit for an infinite sum, the r to the n goes to I'm sorry, forgive me, that's r to the n plus 1 rather. R to the n plus 1, is this n plus 1, as this n plus 1 goes to infinity, if you take a half to the 10th power, it's 1 to the 10th divided. If you take a half to the 10th power, it's 1 to the 10th divided by 2 to the 10th. 2 to the 10th? Are you kidding me? 2 to the 10th is what? I mean, it's 32 times 32. Let me see here. 60. It's 1,024. 1 over 1,024 is tiny. You take it to the million power, it's really tiny. It goes towards 0. So that's where they were getting this. That's why they're saying you can use this. 1 minus r. There are other ways to write this. Certainly other ways to write this. But this is the standard. That's the way they go. Anyway, I got a proof in there as well for you guys. You do this, you play the game, you get v equals 2kq, that we just said. Did they actually, use the formula? That's it. For some reason, I stopped right there. I don't know why I stopped right there, but I mean, you got v equals 2kq. That's that's the hard part. The hard part is the 2kq. Here's 2. Here's k. Here's q. And the q is just one q now because we did the reverse of the distributive property called factorization. We factor everything out of there. The q is 2 microcoulombs. 2 microcoulombs. For some reason, I never gave a final answer on that. Were they given a final answer? Perhaps they weren't when I was looking at it. But it's right there. So definitely, put a final answer on there. It's going to be that. The way this whole thing plays out, I mean, it's going to be 0.02 short of this of 18. when I double this and then double the other one, let me see if I can actually, we might even be able to do this in our heads, you guys. Let's make it easy. 10 to the negative, this is 10 to the negative 6, this is 10 to the positive 9. Multiply the two, you get 10 to the 3. Pretend this is 9. 2 times 9 times 2 is 4 times 9 is 36. Yeah, 36 is too big given what's here. It should be 0.04 short of that. Volts. I hate the V and the V being the same here. One means volts, one is just the symbolic look at that. And you should get, for the voltage here, for the potential, 35,960. So probably didn't write that down there. The big thing, guys, is right here. This has got to be where it's at. They should have given that as an answer for some reason. That's just very strange that they didn't. Yeah, they. Yeah, the answer key is wrong. In fact, their answer key, unless I'm wrong, I don't think that I am. Let me look at it. Their answer key has to be wrong. Now we have to look. I'm almost. They have to be wrong. Actually, there's no. KQ over 3, there's no, that's just simply wrong. This should be the answer in terms of volts, assuming my arithmetic is right, and it should be 2KQ. They've got 2KQ over 3, which to me makes no sense, but that doesn't mean that I'm right. Perhaps they've got it wrong in one place and right in the other. Let's have a look. Give me 1 second, ladies and gentlemen, here. Let me just see. They're alternating. They're alternating what they're doing here. So I'm going to have to. I see the math that they're doing, and it does seem to describe it describes a lot. This does not seem to make any sense to me, ladies and gentlemen. I'm going to have to stay No, this doesn't seem to make any sense of what they're saying. They very well could be correct. The way they have the mathematics set up. Oh, forgive me. Yeah, no, what they're saying makes absolutely a lot of sense. Actually, there is. Yeah, I'm sorry. Forgive me. I was looking at the wrong thing. This is completely correct. Absolutely. 2KQ. For number 79, it becomes a little different dynamic. I don't think I'd even gone there, guys. 79 is a great problem as well. I mean, the way 79 has it, that's where they got the 2/3. For 79, they're saying an infinite number of charges, absolute value, 2 microcoulombs are placed along the x-axis here. What will be the electric potential at x equals 0 if the consecutive charges have alternating signs? Use the mathematical formula for geometric. If they got, that's when it happens. Yeah, this is completely fine. There's nothing wrong here. This is fine. This works. That's the answer for 78. Why did I say 79? Did I write down 79 somewhere? Wrote down the wrong problem, but that's okay. I mean, solve the problem that I wanted to do correctly. Just no, that was 78. Forgive me, guys. That's please when you write this, don't. Yeah, this is fine, not a problem. This is 78. Absolutely. This is 78. Absolutely the right answer. They didn't really. I think in these, the way the answer key solves it for 78 and 79, they just want the symbolism. They just want, in symbolic fashion, and you can write this. But yeah, when they're all working together like that, that's fine. That's absolutely fine. What is going on? And again, we said that's how the whole thing plays out over here. For the heck of it, let me just quickly show you symbolically what they meant by 79, and they're alternating the charges on us. So let me do that really quickly. I'm somewhat pressed for time, but we got this far, might as well answer it, I think, guys. I think it's just a good idea. We got what we got. They ask you to be pretty clever if they change things up on you a little bit. So what they're asking you is, the argument that we gave is essentially the argument that you're going to use even in a more complicated problem like problem number 79. Okay, so 78 was completely correct. 78 is equal to that. When you get to 79, now let's get something different. We've got, okay, some of these you can erase, some you can't, I guess. They're saying there's going to be a bit of a tug of war potential-wise. They're saying the absolute value of the charge is going to be Q at every location, but they're going to alternate. How are they going to alternate? Well, they're doing the same business. They're doing the same business they were doing earlier, and they're saying, okay, now what do you want to do? Well, what we have here they're saying, okay, an infinite number of charges, once again, with absolute value of Q equals 2.0 microcoulombs are placed along the x-axis. Once again, the same location, guys. X equals 1 meters, X equals 2 meters, X equals 4 meters, X equals 8 meters, and so on, as shown in the figure. What will be the electric potential at X equals 0 if the consecutive charges have alternating signs? Now, what will be the electric potential at X equals 0 if the consecutive charges have alternating signs as shown in the figure? Hint, use the mathematical formula for the geometric series. All right, we already proved that. They're saying absolute value of Q is this everywhere, and they're going to alternate. Alternate how? They're going to say Q's the first guy, negative Q's the second guy. First guy, positive Q. First guy, positive Q. Second guy, negative Q. Third guy, positive Q. Fourth guy, negative Q. You get the picture. They're alternating. Now what? Well, this gets a little rough. Or at least it can. We're still going to add them up like this. Yes, carefully. Q is a positive Q. This guy is a negative Q. The fourth guy, third guy rather, with the 4 on the bottom is a positive Q. And here's a negative Q. Are you seeing what I'm seeing? Yeah, still goes on forever, guys, but there's going to be 2 lists here. There's going to be a KQ with a 1 over 1, a 1 over 4. The next comes over to the 16, a 1 over 16. After the 16, there'd be a 32. See, there's what's 4 times smaller? What's 4 times, on the bottom? What's 4 times bigger than 1? 4. What's 4 times bigger than 4? 16. So you're not going to, you're going to skip times 4 on the bottom. 1 here, 1 times 4, 4. 4 times 4, that gets you the 16. 2 times 16 is 32, but that's negative, so 4 times 16 is 64. It's doing that. The other one, you're subtracting KQ. And what's that all about? Well, you got a half, you got an 8. I'll tell you what, it's a little awkward. I guess you're multiplying by 4 over there too, right? So you got a half. Yeah, you're going by 4s too. So you got a half. You got an 8. Right? Let me see here. Yeah, it looks pretty good to me. You multiply that by 4, you got the 32, because the 16 got you a positive. The 32 got you a negative. The 64 got you a positive. 4 times that will get you a negative. Well, you get the picture. You get the picture. What's going on here? This goes to infinity in both places. I tell you what, if you pull the half out of here, wait a minute. Is this 2 twice as big as 1? Is this 4? Is this 2 twice as big as 1? Is this 8 twice as big as 4? Is this 32 twice as big as 16? The 2 is twice what 1 is. The 8 is twice what 4 is. The 32 is twice what 16 is. The 128 is twice what 164 is. What does that mean? It means this. Why don't you pull a 1/2 out of here, and they're all clones of each other again. Yeah, that's kind of neat. There's a lot of ways you could do this. I think I got an easy way to do it. Call this right here, call this infinite sum, hopefully it converges. We know it does. Look, guys, 1/2 plus 1/4 plus 1/8, forgive me, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Didn't we have the 1/2 in there? We had 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 30. Those converted. Those added up. They converged. This is smaller. These are smaller numbers. Of course they're going to converge. If the bigger stuff converged, this will too. I could set it up to be, you could figure out, there's a lot of things you could do, but it's believable that this is going to converge. Let's call all this right here in parentheses, this sum, big X. Call that guy big X, it's the same thing. Call this guy KQ, call it big Y. Call this guy KQ, big Y. So big Y times big X minus 1/2 big Y times big X gives you 1/2. This thing right here equals 1/2. This is a whole thing. It's a whole thing. It's 2 over 2. 2 over 2 minus 1 over 2 is 1/2. It's 1/2 KQ all this, which is 1 plus 1/4. So what's going on here? Yeah, this right here is, let's try to, let me just write it down first. Let me not try to get too ambitious here. 1 plus 1/4 plus 1/16 plus 1/64 plus ... Well, can I make it look like this? Yeah, I got to find out what R is, though. I got an idea. What's a 1/4 taken to the 0 power? 1. What's a 1/4 taken to the 1 power? That's 1/4. Oh, that's good. What's 1/4 squared? It's 1/16. What's 1/4 taken to the 3rd power? 1/64. Okay, I think I got it. That's R. That's the R. The R that we use to do, and you saw me prove it. You saw me prove it using R. Using R as an arbitrary number. R is 1/4 right now. R is 1/4. This thing plus ... Plus ... What does that equal? That's 1 over 1 minus R. In the limit, the top thing goes towards 0 and the 1 stays. It's 1 minus R to the n plus 1, and 1/4 to the very big number is close to 0. So it gets closer and closer to just being 0. 1 minus something close to 0 is close to 1. 1 minus R is 1 minus 1/4. It's 1 minus this, guys. That's the sum. That's the sum we did. It's purposely okay. 1 minus R. 1 minus R. Good. 1 minus R. It's 1/4. We said in this case, R equals 1/4. R equals 1/4. That's all that. What does that mean? V is going to equal all this. What is this? What's 1 divided by this? Well, what's 1 minus 1/4? 1 minus a quarter is 3/4. $1 minus a quarter is 3/4 of a dollar. 1 minus 1/4 is 3/4. 3/4. 1 divided by 3/4, the reciprocal of 3/4 is 4/3. 1 divided by 3/4 is 4/3. We got this. This thing right here, all of this, when you add it, is 4/3. That's 4/3. This is 1/2 KQ. V equals 1/2 KQ. V equals this guy, 1/2 KQ. This guy is this, 4/3. 1/2 KQ times 4/3. The 2 cancels into the 4. You got 2/3 KQ. Makes sense. So it was looking like this. Remember, when they weren't alternating, it was 2 KQ. It was 2 KQ. Here it's not as much. Here it's 2/3 KQ. It makes sense it wouldn't be. One half, 4/3. Again, here it is. Here's the 4, cancels. Here's the 3. 1/2 of 4/3 is 2/3. Two-thirds KQ. Yeah, the other one is 2 KQ. This is 1/3 the size. It makes sense that it would be 1/3 the size, guys. There's a negative. There's negative potential. You know, this is, you know, the negatives are fighting, are creating an issue here. They're making it easier to get closer, I guess you could say. If you were trying to bring something in from here, if you were trying to, you know, if you were trying to bring something in from far away to here, these guys kind of make it easier because they're pulling you and this guy's fighting you. It's a positive test charge. A positive test charge is being repelled by these positive charges, but it's being attracted by these, so it's just not as much potential. It's easier for me to do the work to get here. It still takes work to get to that point, but it takes 1/3 as much work as it took earlier when all of these were positive. Okay, and that was it. I was simply looking at the wrong one, guys. So the solution to 78, unfortunately I may have written, I hope I didn't write 79 down when I was doing it, but where I write 79 down in one of them, I'm really meaning number 78, and that's the correct answer for 78. V was 2 KQ for 78. For 79, we got what we got here. So that's about it. I mean, you're looking at it, you saw it. So I thought the answer key was wrong. On occasion the answer key is wrong. On occasion I'm wrong. On occasion we're all wrong, I guess you could say, right? So, but 78 was 2 KQ, as we said. And 79 was 1/3 of that. And it makes sense it's not going to be as much potential. It's not going to be as much potential because you got the negative charges trying to draw in the positive. The negative charges want to draw in the positive test charge, whereas the positive charges want to fight it. So you still got to do work to get close, to get it to this point from an infinite distance away, for you to bring it to here, you still got to do a lot of work. When these are alternating like this, you got to do this much work, or in other words, there's this much potential that has to be overcome for the positive test charge. Yeah, there's 3 times that amount for the positive test charge to overcome if it's overcoming all of these being positive charges. So that's a big thing. And all of the standard is you're coming in from infinity to the point here, to the point 1 meter away from these guys. And you look at the distance that's there. How much work would be required to do that? Absolutely some fascinating stuff, guys. Dr. Katz does a brilliant job, and the people working on this do really brilliant work related to this stuff. So here's 78, here's 79. That's it. Thanks much. We'll talk again. Have a good one.